Well, welcome. In this video, we're going to be looking at lesson 4.9, and you'll have to excuse my voice as I'm suffering from a cold right now, but hopefully this will work out just fine. But anyhow, we're looking at lesson 4.9. In the previous videos, we've looked at translations, talking about how a translation affects a graph horizontally and vertically because it slides it left, right, or up or down. We've talked about scale changes and how that affects our different sine, cosine, and tangent functions by stretching it horizontally or stretching it vertically or even shrinking it horizontally and vertically. Well, today we're going to look at, well, what happens if you were to combine both a scale change and a translation in the same problem? And that gives us what we call the Graph-Standardization Theorem. Now, to figure out what that theorem would be, let's look at this, what we have here. This is a composition of a translation following a scale change. And that's what the Graph-Standardization Theorem is it's a translation coming after we apply a scale change. Now, remember, from a composition of functions, that means that you take whatever would come first, in this case our scale change, and we're going to plug those values in to our translation, and that'll give us the composition of those two functions. So if we were to do that, this is what it would look like. So here we have our composition of these two functions would be a times x plus h would tell us how the x value is going to be affected, and b times y plus k is going to tell us how the y value is going to be affected. And we could translate this now into an equation to talk about how, for example, the sine function would change if we applied this particular rule to the sine function. And if you do that, we get this equation here. We get y minus k, because if you take the opposite of what happens to the y, so it'll be y minus k, divided by b, because we take and do the opposite of what's happening to the y with the scale change. Since our scale change is multiplying by b, we would do the opposite, divide by b. And for the x's, we're going to replace x with the opposite of what happens with the x, so it'd be x minus our h value from our translation. And for our scale change, we take the opposite of what happens to the x there, which is originally it would be multiplying by a. So in our equation, we would divide by a. So this is our equation. Now we could rewrite this equation to look like what I have up here. So all I've done here, the difference between what's in purple and what's in green, is that what's in green, we're solving for y. So to solve for y, we'd multiply both sides by b, and then we would add k to both sides. So we get y equals b times the sine of x, the quantity x minus h divided by a, that value plus k. Now there's one thing that we always have to remember with these problems, and that is that the coefficient for x always has to be 1. If it's not 1, we have to do a little work ahead of time of factoring out in order for us to get that coefficient to be back to 1. And you'll see an example in a little bit where we're going to have to do just that. Now let's review how we find the amplitude, the period, the phase shift, and the vertical shift. Remember, the amplitude and the period is affected by a scale change, because if we shrink or stretch a graph horizontally or shrink or stretch a graph vertically, that'll change the value of the amplitude, and it'll change the period, how long it takes for it to repeat itself. And so we get the amplitude, remember, from our value for a, and it's always going to be positive. So we say it's the absolute I'm sorry, I said that wrong. It's going to be our value from b. And it's always going to be positive, so it's going to be the absolute value of b. And the period, again, is how the graph is being affected horizontally, which we use our value for a. So if originally our graph has a period of 2 pi, we would take 2 pi times our value for a. Now the only difference is if we're working with tangents. Remember, for a tangent, the period would be a. I'm sorry, it would be pi. So we just take pi times whatever the absolute value of b, I can't speak, would be the absolute value of a times pi would give us our period for a tangent. And our phase shift and our vertical shift, that's affected by our translations. So if we're moving the graph left or right, remember we call that your phase shift. So that is going to be our h value in our equation. And our vertical shift is going to be exactly as it sounds. It's how the graph is affected vertically, which is the k portion in our equation. So this doesn't make sense unless we start to look at some examples. So let's look at some examples now so we can see how we're going to combine everything that we've talked about so far with our translations and our scale changes. Okay, so let's look at this first example. In this first example, we have the equation y equals 3 times the sine of x minus 3 pi, all divided by 4, and then we're subtracting 5. Now, looking at the equation like this, it's really hard for me to know what's going on with the graph. So that's why it's important for us to pull apart from this what our translation and scale change are. So let's start with the translation. The translation here, we look at the x, and we see what's happening with the x. We have x minus 3 pi. So remember, for our translation, we take the opposite of that. So it'll be x plus 3 pi. For the y is already by itself, so we take the minus 5 as it is. So just be y minus 5. For our scale change, we're going to take and look at, again, what's happening with the x. Now, with the x, we have x minus 3 pi divided by 4. So the scale change is that we're dividing by 4 in our equation. So for the rule for our scale change, we take the opposite of that. So it'll be 4 times x. For our y value, again, the y is by itself. So with that 3 there, that 3, we can write it as it is. Just be 3 times y. So again, looking at the equation, it was hard for me to know what was going on with the graph. We're now pulling this apart. I can see that the graph is going to move 3 pi units to the right, and it's going to move down 5 units. It's also going to be stretched horizontally by 4, and it's going to be stretched vertically by 3. Now the next thing I'm going to find is I'm going to figure out what's using this information. I'm going to find my amplitude, my period, my phase shift, and vertical shift. Remember, your amplitude and period are affected by your scale change. So that's where we're going to look to find out what our amplitude and period are. So the fact that my amplitude, or my graph, is going to be stretched vertically by 3 means my amplitude, instead of going between 1 and negative 1, is going to go between 3 and negative 3, meaning my amplitude is going to be 3. Remember, we get that from our value for A here. To figure out what our period is, remember, it's being stretched horizontally by 4. That means it's going to be 4 times larger than it was before horizontally, where originally our period was 2 pi. 4 times that would be 8 pi. So again, we get that by taking 2 pi times 4, because it's being stretched by 4 horizontally. Now, the phase shift and the vertical shift, we get those from our translation. Well, the phase shift, remember, is how our graph is moving horizontally. It's moving to the right 3 pi units. So we'd say the phase shift is 3 pi. It's moving down 5, so we would say the vertical shift is negative 5. And that's how we can draw out all of our information from our equation. So I want you guys to try the same process now for this next example. I want you to figure out what the translation and scale change would be. Then use that to figure out what your amplitude, the period, the phase shift, and vertical shift would be for that equation. So go ahead and pause the video and hit play when you're ready to check to see if you have the correct answer. Okay, let's see how you did. You should have gotten, as your translation, x plus pi and y plus 3, so it's moving to the right pi units and up 3 units. For your scale change, you should have gotten 5x and 4y, so it's being stretched horizontally by 5 and vertically by 4. So your amplitude then would be 4. Your period would be 5 times what it would be originally, so 5 times 2 pi is 10 pi. And your phase shift would be pi, so it's moving to the right pi units. Your vertical shift would be 3, so it's moving up 3 units. Well, let's make this a little bit trickier. Now, if you notice with both of these, your coefficient for x was 1. What happens if it's not 1? What happens if it's a situation like these where we have 3 as your coefficient for your x? Well, that's going to require us to do a little bit of work to get it set up. So what we're going to have to do is we're going to have to factor out a 3 from that parentheses in order to get the coefficient there for the x to be 1. But that's going to be a little bit trickier. So it's going to be tricky to know what it's going to be for the pi, because here we have, again, we're factoring out a 3. So for the first term, it's pretty obvious that if I factor out a 3, I'm just going to be left with x. Basically, factoring out a 3 means we're dividing by 3 from the inside of our parentheses. So 3 divided by 3 is 1, so we're left with 1x. Well, since I don't have a 3 to factor out with the pi, I'd be left with just pi over 3. And if that confuses you, just know that when we're trying to figure, if you were to go backwards and we distributed the 3 through,
you'd get 3x, which is what we had originally, and 3 times pi over 3 would be pi. So if I had 7x, I'd have to factor out a 7. Well, that means that I'd be left with pi over 7. So hopefully you get the idea. So now we have an equation that we can work with. So we're going to figure out what our translation would be here. So again, the translation for this would be x plus pi over 3. And the y would be minus 2. Our scale change for this one would we would take the opposite of what happens to the x. Now here we were multiplying by 3 times that quantity, so it's going to be 1/3 x. Now you might say, well, wait a minute. Why couldn't we just left it as 3? Why did we have to factor anything out? Because our scale change is still going to be 1/3. Well, if we left it the way it was, your translation is what's affected. Because if we had left it the way it was, you would say that your translation would be moving to the right pi units, when in reality it's moving only to the right pi over 3 units. So that's why that 3 is really important to factor out. And then the y value, or for the scale change for your y, since we had a 6 out in front there, that would just be 6y. So now we can figure out what the amplitude and period would be from our scale change. So our amplitude would be 6. Our period would be 1/3 of what it would be originally. So for the cosine function, our period would be 2 pi. So 1/3 of 2 pi would be 2 pi over 3. And for our phase shift and for our vertical shift, again, we're going to get those from our translation. So then we would look up, our phase shift would just be pi over 3. And our vertical shift would be that it would move down 2 units, so it would be -2. So now why don't you guys try this next one on your own. So why don't you pause the video and hit play when you're ready to check your answer for this equation, y equals 2 times the sine of 3x plus pi. Again, you don't have a coefficient of 1, so you have to start by factoring out a 3, just like we did in the previous one. So why don't you guys try this one, hit play when you're ready to check your answer. Okay, let's see how you did here. So you should have factored out a 3, so you'd have 3 times, in parentheses, x plus pi over 3. So giving us a translation then of x minus pi over 3. Now the tricky thing here is for your translation, there's nothing over here. So that tells us that it's not being moved at all vertically, so the y stays the same. The scale change is that it would be, well, they take the reciprocal of 3, it would be 1/3. And the y, since the y is already by itself, we just use the 2, so it would be 2 times y. So your amplitude would be 2, your period again would be 2 pi over 3, because it's 1/3 of the original period, which would be 2 pi. 1/3 of 2 pi is 2 pi over 3. Your phase shift would be negative pi over 3, so it's moving to the left pi over 3 units. And your vertical shift would be 0, because it's not moving up or down at all. So that's what you do if you have a coefficient that's not 1. Well, let's look at one last example where we have a situation where we have where they're going to give us the amplitude, the period, the phase shift, and the vertical shift. We're not going to bother with the story problems right now. If you have my notes, we'll just end with this example. So first off, you want to recall from the beginning of our notes, we had this equation, y equals b times the sine of the quantity x minus h, all divided by a plus k. Now, we're going to plug this information in, but we first have to figure out what's our values for a, b, h, and k. Let's start with the phase shift and the vertical shift, because that's going to be from your translation. So phase shift, that's going to be our value for h in this equation. Our vertical shift then is going to be our value for k in that equation. Our amplitude, remember that's from your scale change. It's not the a in this equation. Don't get confused by that. A lot of people think that amplitude would be a, but remember your amplitude is how y is being affected, which would be b in your equation. Now I saved period for last for a reason, because it's not just as easy as just saying the period is pi. Because remember, to find the period, to find out what pi is, we first have to take 2 pi times the absolute value of a, gives us our period, which is pi. So to figure out what our value for a would be, I'd have to divide both sides by 2 pi. So our value for a is not pi. Our value for a here would be 1/2. Because if I take pi divided by pi over 2, you get the pi's canceling out. So you'd have 1 over 2 left over. Which makes sense for this one, because if originally the function had a period of 2 pi, pi is half that. But it's not as obvious if the period was, let's say, 2 pi over 3 or something like that. So you want to make sure that you know to find the period, we have to set up this equation to say 2 pi times a gives us the value of pi. So you solve that equation for a. Now we're going to plug all these pieces into this equation. So our answer would be y equals our value for b, which is 4, times the sign of the quantity, x minus h, which is pi over 2, divided by a, which we found is 1/2, plus k, well, k is -1, so it'll be -1. Now, technically, it's not okay to leave it like this because we cannot have a fraction inside of a fraction. So we should rewrite this as y equals 4 times the sign. In order to get rid of this fraction in our denominator, we multiply the numerator by the reciprocal of the denominator. Well, the reciprocal of 1/2 is 2. So we're going to take that whole numerator and multiply it times 2. So it's not 2x minus pi over 2 because you have to, it's the whole, since originally it was a whole fraction or whole numerator divided by 1/2, we have to make sure to multiply the whole numerator by the reciprocal of 2. We don't actually distribute it because remember then we'd have a coefficient for x that would not be 1. So we leave it like this. So there you have it. That is the notes for lesson 4.9 for how to use the Graph-Standardization Theorem. So hopefully you have a better understanding of how to apply the concepts that we just talked about to your assignment. And hopefully my scratchy voice here with having a cold hasn't affected things too much for you. But with that, good luck now as you work on your assignment.